All right, let's talk about a technology you've probably heard buzzing around, but maybe don't fully get, Docker. We're going to demystify it, break down exactly what it is, how it works, and maybe most importantly, why it's become this absolute must-have tool for pretty much anyone who builds or runs software today. And we have to start right here with this phrase, because if you've ever worked with code, you've either said this or you've heard it. It's that classic hair-pulling moment, right? Your project runs perfectly on your laptop, but the second you send it to a colleague, it just breaks. This one sentence perfectly captures a huge, fundamental problem we've been trying to solve for decades. And that problem has a name, a pretty dramatic one: dependency hell. This is the frustrating reality of trying to get software to work when every single computer is a unique little snowflake. It fails because of dependencies, all the other little bits of software, the libraries, the tools that your code needs to function. Your machine has version 1.2, theirs has 1.3, and boom, everything grinds to a halt. So how do we escape this mess? Well, the answer is a really elegant idea called containerization, and Docker is by far the most popular tool to do it. The core idea is simple. Stop trying to move the software between messy, different environments. Instead, let's package the software up inside a perfect, standardized magic box that can run anywhere. And that magic box is what we call a container. Think of it as a perfect, self-contained little bubble. It doesn't just hold your code, it holds everything your code needs to run. All the right versions of all the right tools and libraries, they're all packed in there together, guaranteeing that it will run the exact same way every single time, no matter whose computer it's on. Now, right about now, you might be thinking, hold on, this sounds a whole lot like a virtual machine or a VM. And you're not wrong. They both create these isolated spaces for software to run. It's a really fair question, but there is a crucial difference that makes containers a total game changer. And that difference really comes down to efficiency. A virtual machine is a heavyweight beast. Why? Because it has to pretend to be an entirely separate computer, which means it bundles a full copy of an entire operating system inside it. We're talking tens of gigabytes, and they take a long time to boot up. But a container? A container is clever. It's incredibly lightweight because it shares the core part of the host computer's operating system, what's called the kernel. Because it's just sharing, not duplicating, it's way smaller and starts up in a flash. Okay, so to really get how Docker builds these magic boxes, let's use a super simple analogy that I think makes it all click: a restaurant kitchen. There are really just three key pieces you need to know about. It all starts with the Docker file. This is quite literally the recipe for your application. It's just a plain text file where you write out, step by step, what needs to go in the box. You know, start with the basic Linux system, then install Python, then copy my code files over. It's the blueprint. Now, when you follow the instructions in that recipe, you bake it, and you create an image. An image is like a standardized dish on the menu. It's the pre-made, ready-to-go template. It's sitting there, perfected, but it's not actually a hot meal on a plate yet. It's just on the menu, ready to be ordered. And finally, when you actually run that image, you get a container. The container is the final dish, served hot and ready for you to use. It's the live running version of your application. And just like a kitchen can send out hundreds of plates of its most popular dish, you can launch tons of identical containers from just one single image. And that brings us to the two most fundamental commands you'll use. First, Docker pull. That's like ordering from the menu. It goes out and downloads the image you want. Then, Docker run. Well, that serves the dish. It takes that image and fires up a running container from it. It's that simple. Okay, so we've established that these containers are nicely isolated from your computer, which is great for consistency. But, that very isolation creates a really practical problem we need to solve. I mean, think about it. If the whole point is to keep the container sealed off from the rest of your machine, how in the world do you get your actual files, your data, your code, your documents into the container so it can actually do some work? The answer is a really cool trick called a bind mount. You can think of it like a portal or a window. It creates a direct, live connection between a folder on your computer, we call that the host, and a folder inside the isolated container, the guest. They are linked. You change a file on the outside, it instantly changes on the inside, and vice versa. Now, when you're setting up this portal, you have to get the command just right. The syntax is absolutely crucial, and the order is what matters most. It is always the path on the outside, on your machine, first, then a colon, then the path on the inside of the container. Get that backwards, and you'll be scratching your head for a while. So now that we've seen how it all works under the hood, let's zoom back out. Let's talk about the big payoff,
Why has learning this stuff become such a game changer for so many people?
Well, here are the real gems. You get true, perfect reproducibility. That's a huge deal for science and for business. You get a single, standard environment that you can just hand off to anyone. And that means your container is portable. It'll run on your laptop, your colleague's Mac, a server in the cloud, anywhere Docker is installed. And best of all, you can finally say goodbye to dependency hell.
And look, this isn't just for Silicon Valley startups. This is having a massive impact in really high-stakes fields. Take scientific research, like neuroimaging. Scientists are now packaging their complex data analysis software into Docker containers. Why? So a researcher in another lab, halfway across the world, can rerun their analysis and get the exact same results. That's the bedrock of good science, and Docker makes it possible.
And that kind of brings us to the final thought here. What Docker really does is remove friction. It tears down one of the biggest, most annoying barriers to creating and sharing software. It makes building really complex things more accessible than it has ever been before. And that leaves us with a really exciting question for the future. Now that we can build almost anything to run almost anywhere, what amazing things are we going to build next?